Welcome to this instructional video on process capability index and ratio. Join us as we dive into the essential of statistical process control techniques. So, understanding capability. Several methodologies are available out there to calculate or evaluate capabilities. So the first one is process capability index and ratio. The second one here is process performance. This can be measured via process performance index. This one and process performance ratio. This one. Machine capability can be gauged through machine capability index and machine capability ratio. This discussion will focus exclusively on process capability index and process capability ratio under the assumption that all prerequisite conditions have been satisfied. For example, we will assume that the process under consideration is assumed to be in statistical control. So now let's define what process capability is. Process capability measures the ability of a process to produce outputs such as goods and services within design specifications. Right. However, being in statistical control does not guarantee that the process will be capable. A process must first be in statistical control and pass all specific capability tests to be deemed capable. Why? Because a process that is in statistical control may not be capable. It depends. So now let's talk about the design specification. Design specification define the acceptable limit for products and service quality. These include the nominal value, we also call it the target, the tolerance, and the upper and lower specification limits. These are calculated based on these values, setting what we call the range for acceptable output. So how do we calculate that? The upper specification limit will then be the nominal value plus the tolerance, and the lower specification limit will be the nominal value minus the tolerance. Okay, so now sigma levels and process capability. So let's see how this works. This table shows critical value associated with sigma levels from 1 year to 6. Right. These values are thresholds for process capability index. Right. A higher sigma level indicates a more capable process. So a process that performs, for example, at 4 sigma is more capable than the one that performs at 2 sigma. The process that performs at 3 sigma is more capable than the process that performs at 1 sigma, and so on and so on. The ideal value here being 6 sigma. Right? Every company dreams to have their process performing at 6 sigma level. Right? So always remember that a process is deemed capable if it is achieved at a process capability index equal or greater than the critical value at that sigma level. For example, if we are assessing the process capability at 4 sigma level, right, the critical value is 1.3. So that process must perform at least at 4 sigma level. So the highlighted part that you see here, the yellow one of that table, shows that at 4 sigma the critical value is 1.33. A process with a Cpk that is 1.3 or more at that level will be considered capable. So in general, 4 sigma is the standard. So we just use 1.33 as our critical value for evaluating process capability. So let's now have a look at the interpretation. How do we interpret that? So if we test our process and the process capability index, which we call here Cpk, is equal to 1.33 or higher than 1.33, we say that, oh, this process passed the Cpk test and this process is capable. If the process capability index Cpk is less than 1.33, we say that, okay, the process failed the test, the Cpk test, and therefore this process is not capable. That's in general what we should remember. Every time you calculate your Cpk, if it is equal to 1.33 or higher than 1.33, the process is capable. If it is less than that, the process is not capable. So now let's see how we link them together. If the process failed the Cpk test, which means it's not capable, then we will calculate the process capability ratio, the Cp, to see what is causing the problem. So remember that the Cp only tests variability. So if the Cp passes the test, right, if the process passes the Cp test, right, then we say that, okay, variability is not what is causing the problem. What is causing the problem is centering. See, if the process failed the Cp test this time, then we're going to say, okay, variability is what is the problem, or it is what made why the process failed the Cpk test. So now that we know the interpretation, let's see how we calculate them. The Cpk is calculated as the minimum of these two values. We calculate this value and the other value, then the minimum of the two will be what we will consider to be our Cpk. So always remember, if we have 1.33 or higher, the process is capable. If we have less, the process is not capable. So now for the Cp. The Cp is the process capability ratio. This is the test that we do after the process failed the process capability index. So first of all, this is the formula, which is the upper specification minus the lower specification divided by 6 sigma. So this part, which is the upper specification minus the lower specification, is what we call the engineering tolerance or the specifications tolerance. So why do we call this process capability ratio, not index? Because it is the ratio of the engineering tolerance to the natural tolerance. The natural tolerance is your 6 sigma here, and the engineering tolerance is the upper specification minus the lower specification, also known as the specification tolerance. So again, now the process have failed the Cpk test, and now we are trying to figure out what is wrong. That's why we are using the Cp test. So now is the process passed the Cp test? We say that, okay, the problem is centering. If the process failed the Cp test, we say, okay, the problem is variability. Again, we use the Cp only if the process has already failed the Cpk test, because the Cpk tests both variability and centering, and this one only tests variability. Right? So what we're going to do now, let's explore an example from a manufacturing facility producing bolts. So we will calculate the upper specification limit and the lower specification limit. That's we have it here. Our upper specification limit is 10.20 and our lower specification limit is 9.8. So just remember that the average was 10.05 and that the standard deviation of this process is 0.04. Against the lower specification limit is 9.8 from here, and the upper specification limit is 10.20. So we put the number in our formula and we come to realize that the process capability index, the Cpk, is we have two values here, 2.08 and 1.25. So the minimum of these two values, 2.08 and 1.25, the minimum is 1.25. So we're going to say, okay, the Cpk here is 1.25, but you can see that 1.25 is less than 1.33. So this process failed the Cpk test. So the process is not capable. So now that the process failed the Cpk test, now we want to figure out what is wrong with that process. And then we're going to go run our process capability ratio test now. So we calculate our process capability ratio, and the result is 1.67, which is higher than 1.33. So our process passed the CP test, the process capability ratio test. So variability is okay. And if variability is okay, so why did that process fail the CP test? Why is the process not capable? Then the problem is centering, because the two most important considerations when it comes to process capability are centering and variability. Now, in conclusion, understanding and calculating the process capability index Cpk and ratio Cp are crucial for quality control in manufacturing and service processes. Thank you for joining us in this comprehensive overview. Stay informed and enhance your operational efficiency with the knowledge from subject matter experts. Thank you so much, and we will talk to you in the next video. Bye-bye.